Continuing with our work in polar form, let's look at a slightly more advanced example where we aren't in our first quadrant. So what happens when we have to do that? What happens to our reference angle in particular? Because that's the main thing that gets a little bit more complicated. But again, it's purely based in our work that we already know from trigonometry. So if I have Z3, I have -2 in the real, -2 in the imaginary, as I have plotted here. I've drawn in my modulus line. So this is my hypotenuse of my triangle is going to be my modulus. So I'm going to draw in effectively my little sketch here to tell me if I didn't have this diagram, this is what I'm going to have to do. And I know that I'm going minus in the real, minus in the imaginary, so I'm going roughly down something like that. It doesn't need to be wildly accurate. Now I've gone to -2, -2. I have my imaginary and my real axis. And I'm going to need to find my angle to the positive real axis, and I'm going to need to find my modulus. And obviously I have this drawn out in a nicer diagram here. So I'm going to find my modulus first. So if I look at my triangle that I've got going on here, I have a little triangle. I'll write it in the same orientation so I don't get myself confused with things. I've gone 2 and 2, and in a minute I'm going to look for my reference angle alpha 3 down here. But for right now I'm looking for my modulus of Z3, which again is just the hypotenuse of a triangle. So I have that squared is equal to 2 squared plus 2 squared. I do not care about the direction at all here. This is merely a magnitude. That's why my diagram does not include I and it does not include the minuses, because I'm just looking at a triangle of that shape. And when I do that out, I will get the modulus of Z3 is equal to 2√2. Now, what is my argument going to be? So what's my argument going to be? Argument again is my name for theta, and that is going to require me to find my reference angle first. So my reference angle, it's the first thing that I am going to need to find, and that's my alpha 3 in my diagram here. Drawing these triangles helps enormously for these types of situations. Keeping track of find my reference angle, then draw my bigger diagram, often my unit circle, to figure out what quadrant I'm in, and therefore what the overall angle, my theta, is going to be. So I have my reference angle, and I know that at tan of my reference angle, alpha 3, is going to be equal to 2/2, which is equal to 1. So I get inverse tan of both sides, and I get tan inverse of 1. We can work in degrees again this time, because we already practiced our radians. That ends up being 45 degrees. So I've gone 45 degrees down here. Now the fact that you can recognize this is an isosceles right angle triangle, you'll immediately know it's 45 degrees, but we should still show our steps. So we know that we are at 45 degrees, but that's not the angle to the positive real axis. That's going up to the negative real axis. So we need to figure out what quadrant we're in to figure out what our overall theta should be. Well, we're down here. We're in the third quadrant. So we have gone around 180 degrees when we were in the third quadrant, and then we've gone 45 degrees more. So our angle that we are looking for, theta 3, is going to be 180 degrees plus 45 degrees, which is going to bring us around to 225 degrees overall. Again, this is pure trigonometry work, and you can see a lot of this complex numbers brings together algebra and trigonometry a lot. So I now have my angle and I have my modulus. So now it's just a matter of subbing in. I have Z3 is going to be my modulus of Z3 on cos open bracket, cos of my theta 3 plus I sine of theta 3, and I sub in. Again, a version of this formula is our de Moivre's theorem on page 20 in our log tables. And I sub in and I get 2 root 2 cos of 225 plus I sine 225. And I close both of my brackets there. And that is all I need for turning a number into polar form. Again, this concept of the angle that we are to the real axis is now explicit, and our distance from the origin is now explicit. And for a lot of the work that we want to think about in terms of complex numbers, rotation is key, and that's why this polar form is going to help us so much very soon. And that's what we need for now.